Once again, hello everyone. Welcome to the second day of the Computer Security Foundation Symposium. I'm delighted to introduce today's invited speaker. Peter Sewell is a professor of computer science at University of Cambridge Computer Laboratory. He has studied at Cambridge and Oxford and received his PhD degree from University of Edinburgh. Peter is famous for building mathematically precise and usable semantics of real-world low-level programming languages, interfaces, and other systems. His foundational and applied research helps us make sense of these systems, despite their complex, inconsistent, and often incomplete specifications. It helps us verify the properties of those systems, fix their shortcomings, and of course, improve them. Through the Cerberus project, he has developed semantics for a significant fragment of the C programming language, with the focus on the semantics of pointers and memory objects. This research has discovered numerous issues and discrepancies between standards and implementations, and the impact of the research is visible in the current and future C and C++ standards that Peter and his colleagues helped significantly improve by collaboration with the standards working groups. In another line of research, Peter and his colleagues are developing mathematically precise semantics for multiprocessor programs with the focus on relaxed memory concurrency models. They are building and reasoning about models for different instruction set architectures and for programming instructions in C and C++. I also have to mention his work on the semantics of low-level network protocols, his work on type-safe distributed languages, and finally, his research on secure composition and security policies that was published at CSF back when CSF was still a workshop. Today, he's going to be talking about the hardware-software interface, namely the CHERI architecture, that extends standard instruction set architectures with security features. Peter, the floor is yours.
Okay, thank you very much for that introduction and also for the invitation to be here. It's, as you say, a long time since I was at CSFW. It was a pleasure then, it's a pleasure now. So I'm going to be telling you something about CHERI. As you can see from the enormous number of authors here, CHERI is a pretty substantial project. So more particularly, I'm going to be giving you an introduction to CHERI as a whole and a little bit of an introduction to the industry prototype version of CHERI, Morello, which is currently being developed by ARM. And then going back to computer security foundations, I'll talk a bit about what some of us have been doing to establish precise semantics for that and to verify that it does actually give you some of the security properties that it's supposed to give. So CHERI as a whole, as I said, it's a vast enterprise led by Robert Watson, Simon Moore, myself, all at Cambridge, Peter Neumann at SRI, Ian Stark at Edinburgh, and with many colleagues now in ARM and others in the University of Cambridge and SRI. These people at the top, Thomas Bauer-Rice, Brian Campbell, Thomas Sewell, Kinderland Nienhaus, Alistair Armstrong, Prashant, Robert Norton, Alexandra. These are the people who have been most involved in the semantics and verification work that I'm going to talk about in the second part. Okay, so Computer Security Foundations Workshop. So foundations then are probably something that all of us here think are very important. Right? If we get this wrong, then our beautiful infrastructure, it leans, and beyond leaning, very, very often it collapses. Right? So we all know here, I think, we know very well some of the root causes of this, the legacy design choices from the 1970s and so on, and the standard industry practice. We have systems languages that don't enforce memory protection, hardware that only enforces protection at a very coarse granularity using virtual memory, and test and debug development methods that can never provide assurance. And all of this is just ingrained in what we work with. So that means, of course, that programming errors, they often give exploitable vulnerabilities, and recent estimates, surprisingly similar from Microsoft and from the Chromium project, estimate about 70% of the serious cases that they have to deal with are due to some kind of memory safety violation. Yeah. And just to make this totally concrete, here's a little tiny C program, which I'll come back to later, to explain CHERI. So here we have some code. It's got two global variables, and one of them is supposed to be a secret key. Well, there's no occurrence of the identifier secret key in the body of this code, so you might think as a programmer that it would be in fact safe. What does the code do? Well, it constructs a pointer to some other variable, x, and then it increments that pointer, perfectly allowed in C. But in some executions, the result of that might be the same as the virtual address of the secret key. And therefore, in an implementation, this print would cheerfully leak the value. Okay, so our foundations, therefore, are not at all good. Our foundations are terrible. And if your foundations are terrible, and you're not prepared to just demolish the whole building and start again, which we are not for the software and hardware and educational infrastructure that is the entire world of computing, if we can't tear all of that down and start again, then we have to underpin the foundations with something better. And indeed, we need to do this because the original foundation, while maybe good enough for the 1970s, is not good enough now. So we have many options if we want to do that. In principle, we could just get everyone to stop making programming errors. That totally works. We could rewrite all the critical system software in the world in memory-safe languages. That is more possible now than it was 10 years ago, but it's still a tough ask. We could verify all the critical system software. That's again, it's becoming possible to verify some critical system software pragmatically, but still a tough ask. We can use better bug finding tools. Certainly, those are now getting much better developed. They certainly help. They certainly don't solve the problem. We can do whatever partial mitigations we can think of, SFI systems and what have you. Certainly helps, doesn't solve the problem. Or something we think of less often is that we can redesign the architectural interface between hardware and software and redesign the hardware and redesign the software a bit to provide better protection. And that is essentially what CHERI is trying to do. Right? So CHERI is at its heart a set of architecture extensions to support better hardware enforcement, both of fine-grained memory protection and of secure encapsulation. And actually, you can use either of these in different mixtures as you see fit. And the way it does this is by taking an old idea of capabilities, hardware capabilities in particular, and making them actually viable in modern systems. So these are unforgeable capabilities. The whole project started maybe 10 years ago by Robert and Peter Neumann and Simon. And then a few years after that, some of my colleagues and I joined along to add some semantics and verification to the thing. So, basic idea of CHERI then, going back to that example program. Here we have this thing, which in ISO-C, actually in ISO-C, this is undefined behavior. But in the C implementations, that undefined behavior is, as it were, implemented by code that just leaks the secret. It just reads from a machine word virtual address, which ends up being the same as that of the secret key. In CHERI-C, well, what do we do? So you see, instead of this pointer value that on the left was just a virtual address, in CHERI-C, it's got more data in it. It's still got a virtual address, and that value is the same, but it's also got the base and the length of the allocation that this pointer value is allowed to access, and some permissions, and actually some other data too, which I'm going to skip over. Right. So this is a bit bigger. That was maybe a 64-bit value. This is a 128-bit value, and these are compressed in a devious way to make that possible. But having that data there in the pointer value means that whenever you do an access, you can do a fast access time check that the virtual address that you're using is within the footprint of the allocation that you think you're supposed to be allowed to use. And if that doesn't match, well, you can fault. So you can fail safe. Okay, there's some other things going on here. So if that was all you had, then trivially in C, you could overwrite this capability with some other data and thereby a bug or an intentional exploit in some piece of code would let you ultimately would ultimately lead to the same problem, right? It would let information be leaked. So we need to enforce integrity of these, and the hardware does that by keeping track for each capability also an extra kind of magical bit, which is not conventionally addressed and which is preserved by any legitimate operation on capabilities, but automatically cleared by the hardware by any other operation. For example, if you write to the individual bytes of the capability, the hardware will clear that tag. So you know capabilities with the tag set are valid and all the others are not valid. When the hardware boots up, it will give you a universal capability, and then the system software, the hypervisor and the operating system and the allocator and the linker for globals and the compiler runtime for locals will gradually narrow these capabilities so that you're always working with a pretty small set of permissions. Okay, so this is great. This gives us fine-grained enforcement of memory safety. We get a guarantee, more or less, that we'll trap if we do something like that. Let me just go over these design decisions again. I think I already stated all of these, except that I missed out this second one. I didn't make that explicit. So the design of a CHERI ISA, it lets code shrink capabilities, but there are no instructions that let you grow capabilities or merge capabilities even. Right? So that's fundamental to the security of the whole thing. And then there are some other design decisions which are more fuzzy, but are very important to make this deployable. So you can use capabilities for all pointers, and that's what you get by default in CHERI C++ or CHERI C. This is what we call pure capability CHERI C. Or you can use them just sometimes in a hybrid mode. Usually you want the former, sometimes you want the latter. The whole thing, it coexists nicely with existing C and C++ code, nicely with existing ISAs, and nicely with existing virtual memory machinery. So you can use both, or you could use just capabilities, or you could turn capabilities off. There's also some other machinery that I'm not going to talk about in much detail. There's some machinery, extra kinds of capabilities, sealed capabilities for secure encapsulation. And what I'm going to talk about is mostly talking about spatial memory safety, but there's also machinery and software support for temporal memory safety to some extent. I'm going to skip those two today. Okay, so looking then at the two goals again, so for fine-grained memory protection, this is using capabilities instead of pointers, instead of integer pointers throughout your address space. And that means both language level pointers, so C language pointers visible to the programmer to stack and heap allocations and globals and subobjects and what have you, but also language implementation pointers, stack pointers, return addresses, vtable pointers, and so on. So if you have like reasonably civilized, well-behaved C or C++, you get all this protection for free just by recompiling. If you have low-level C code, which is doing manipulations of pointer bits or what have you, you may need to adapt that C code a little bit. We'll come back to that later. Well, basically, it's just a recompile. But sorry, in the first case, it's just a recompile. So then the other thing CHERI gives you is machinery for secure encapsulation. And this might be at a larger granularity or at a smaller, but this is really escaping the limitations of virtual memory protection. Right? So virtual memory protection is great. It's the only, in some sense, the only computer security that really works, but it doesn't scale well. So if you have even too many browser tabs, then the performance might start to go bad on you. And having many small granules of encapsulation just doesn't work. So with CHERI, you can do this at a fine grain. You can also combine with the previous memory protection or not, as you wish. And because this isn't an MMU-based mechanism, the load on the MMU is relatively minor. So you can have a very low domain crossing cost. So you can actually get a performance win as well as increased security in some circumstances. Okay, so CHERI is designed following a very old principle. It's letting software be organized in such a way that more or less you have the least privilege required to do the job. Also designed on a new principle, the principle of intentional use. When you use a capability, you have to make explicit in the instruction or whatever which capability you're using. There's no search or inference going on. That means you more or less always know what you're doing. And then there's been a strong emphasis throughout on making this feasibly adoptable. And we'll be talking a lot more about that in the next few minutes. So it's a project, originally an academic project, well, academic Cambridge and SRI project for about 9 or 10 years, funded mostly by DARPA, also by UK funding, a bit from Google, DeepMind, ARM, HP. And it has several strands. So the heart of it is architecture design. So we designed extensions of the MIPS and the RISC-V architecture spec that include the machinery that I've been talking about. And then there have been hardware implementations. So these are FPGA implementations running on a couple of kinds of FPGA. You can run these on Amazon these days. And this is mostly led by Simon Moore. So these are real working processes. There's also a QEMU emulator for the architecture. And then there's a software stack, which is really Robert Watson. I mean, both, sorry, I should say the architecture design is sort of Robert and Simon and all of a large team of people, as are these other things. Then there's a software stack, which is especially Robert's domain, in which we've ported and extended compilers, excuse me, linkers, debuggers, the whole FreeBSD operating system, the FreeRTOS operating system, to support and to use these features. So it's really been tested with a substantial body of software. And then last is the semantics and verification side, which I'll come back to towards the end of the talk. Okay, so that all sounds good. Is it actually adoptable? Is it more than an academic project in that sense? Well, the question for that is, does it provide good protection at acceptable performance cost and acceptable software porting cost? So we did a lot of academic evaluation. It's very encouraging. ARM and several other large companies are very interested and very involved. But none of this academic evaluation could really tell you how well it works in the context of a modern high-end superscalar core. So these hardware implementations that we did, these are non-trivial cores. Like, this is a 64-bit pipeline thing, but it's not an ARM mobile phone processor grade core. And without data from that kind of experiment, it turns out to be very hard to get industry to commit. Right? We're asking here not for a huge change to existing architecture and software, but certainly a substantial change. And that means one wants to be quite sure that it's going to work. And that means you need an industrial scale demonstrator. But it's quite hard to get the investment of funds to build an industrial scale demonstrator that might cost you 50 to 100 million pounds maybe, without evidence that it's going to work. So you're stuck in a rather annoying chicken and egg problem. But we were stuck a few years ago. We were looking around, talking with ARM and others about what we could do, when up popped a call for expressions of interest in a UK government funding programme funded by the Industrial Strategy Challenge Fund, which exactly exists in order to enable non-trivial transition of work into industry. And we looked at this and we said, well, that seems to actually just about match our situation. We need some pump priming funding to get an industry demonstrator going. And we sent off a little expression of interest, which was just like one page. And after considerably more work and quite a delay, and somewhat to our surprise, out popped this 5-year Digital Security by Design program, which is a UK government funded program to the tune of 70 million and about 117 million of industrial match funding from various large companies, mostly, well, to a large extent ARM. And the purpose of all of this at the heart is to create a prototype version of a CHERI ARM. And this is called Morello. So it's a prototype architecture and processor implementation and SOC and development board and software and proofs, all scaling up the CHERI ideas to the full ARM A-class processor context. So this is the ARM architecture that runs in all of your mobile phones. So there's lots within this program. There's actually a lot of other work going on too. There's a business-led demonstrator. There are a bunch of individual research projects by other institutions. There are a bunch of SMEs doing sort of deployment experiments. There's some social science about adoption, a lot of things. But let me just focus on the development of Morello itself for the next few minutes, the technology platform prototype. So this is a collaboration mostly by ARM and then with Cambridge, the University of Edinburgh and Linaro. Okay, it's got a lot of pieces. First, there's the architecture. So the ARM architecture spec is a PDF of about 8,500 pages. And within that, there's, or underlying that, there's maybe 50 to 100,000 lines of essentially of code that define the behavior of instructions and the translation table walk and all of that stuff. Right. So for Morello, there's an extension of this architecture spec with the CHERI ideas. It changes some instructions, it adds some instructions, it changes the architected state a bit. And there is similarly a spec in the ARM internal instruction definition language, ASL, of exactly what the behavior of those instructions is. Then there are software emulators, a platform model produced by ARM, so that's a functional simulator, and a version of QEMU adapted to this being developed at Cambridge. There's the hardware implementation. So this is, in a sense, the main event. So this is actual hardware being developed by ARM. It's been designed by ARM. In fact, it taped out about a month ago or so. It's very exciting. It's now being fabricated. Then there are software stacks, CHERI, Clang, and LLVM, C, C++, linkers, debuggers, CHERI BSD, and a range of applications, and a bunch of other things. A bunch of things here have been prototyped, including a memory-safe kernel for CHERI BSD, so a full memory-safe operating system kernel, and work on temporal safety and compartmentalization. And then there's further work on software at a slightly earlier stage, and this is mostly driven by ARM and Linaro, working on the GNU toolchain and on enabling CHERI work in Android and Linux. And so that is not yet at the point, not at all at the point of a complete CHERI-ified Linux kernel, but it's enabling some work that will be necessary to get there. And then again, some semantics and verification here too, which again, I will come back to in a few moments. So that's the Morello program as a whole. So now I'll use some slides from Richard Grissenthwaite and Mark Inskip at ARM, and a few slides from Robert, talking a little bit more in detail about the hardware and the software of Morello. I'll go over these fairly quickly for the sake of time, but the slides will be online, so maybe these will be useful as a reference. So the idea of all of this is that CHERI is a thing, sorry, Morello is a thing that people will be able to evaluate and to do research above. So documentation and support and the existence of artifacts is very important. And I think all the artifacts that I'm talking about will be or are already available. Okay, so first the hardware. This is a slide from Richard Grissenthwaite from the beginning of the program, actually. This dates back to 2019. The important thing here about Morello is that this is something that ARM don't usually do. Right? This is a prototype experimental architecture. So it's not, as it is, a commercial product. They're not going to make very many of them, of the order of 1,000 boards total, perhaps. The idea is that that's enough for evaluation, but this is not right now an extension to the mainline ARM architecture, and there is, as it says clearly at the bottom here, there's no commitment to binary compatibility for the future. We expect and hope, if it's successful, then the ideas, quite a lot of the detailed design would be carried forward into the mainline architecture, but we're not at that point yet. More recent updates from Mark Inskip, program director for this inside ARM. So just to give you a clue, so inside the board, there's an SoC. The SoC has 4 CPUs, 2 clusters each of these Rainier CPUs, which are adaptations of the previous Neoverse N1. It's got a grown-up interconnect. It's got DRAM interfaces, PCI interfaces, a mid-range GPU, so it will be possible to run Android on it on a pretty standard-looking board. Apparently, it will look like this. I say will look like this. That SoC says Morello SOC on the front, but that has been photoshopped in just for the time being. As I said, it's being fabbed right now. If you want access to one of these, it might be possible. So the supplies are limited, but if you're already part of DSPD, you should already know how to get access. If you're a UK institution, then there is some application process you can go through. Or if you're not, then it might be possible to buy them directly from ARM, more or less at cost. And the incremental cost is about 5K. If you want to do that, then best email us and we can introduce you to the right people. Morello software, so now a few slides from Robert. So I don't want to talk about this in too much detail, but it's basically a complete software stack, right? From compiler, hypervisor being developed at the moment, and then FreeBSD adapted to CHERI. So this is, the operating system used not so much on the desktop, but used widely in enterprises for all kinds of things. And then a suite of open source applications, including WebKit and Python and OpenSSH and Nginx and what have you. So all of this is being, or has been, ported and adapted to use CHERI. I'll just leave this here so you can look at it. If you want to understand CHERI, C and C++ in an informal sense, then one should look at this programming guide, which is a tech report on our web pages. CHERI BSD. So user space and kernel spatial safety, work in progress on user space temporal safety, all kinds of things going on. And the QEMU emulator, so this is mature and fast for CHERI RISC-V, and for Morello, it's in progress right now. It already kind of works. I think bugs are still being found, but for experimental use, one could start trying to use this now. If you want to try and install all of this, we've gone to some lengths to make it as easy as we can. So there is one build tool that will install, build, or run all of this machinery if you want. So it's relatively easy to get started with. On the ARM software side, is just a little bit more detail for reference about the ARM software plans. Okay, so the point of this whole program is to enable industrial scale evaluation of CHERI. And if it works, then the evidence from that will be what's needed to drive potential mass market adoption. So we're not yet remotely at the point where we can do that. That will need, to have the hardware in our hands and to do that evaluation work. There's a few things one can say already. So first, what are the dimensions? Well, the performance cost has to be okay, energy usage, speed. The software adaptation cost has to be okay, and it has to actually give you increased security. So for performance cost, well, we don't know, we can't know. We have kind of encouraging data from the academic experiments, but you need both the hardware and you need a mature software stack. So you can't get meaningful performance data unless, for example, you have adapted the compilers to correctly optimize and not optimize in the ways that CHERI lets you. So that all will take some time. The software adaptation cost, though, that we can say something about already from all of this work that I've just described. So this is work, this is some data from adapting CHERI BSD. So this is both the kernel and the user space. And you can see it's quite a lot of lines of code, right? About 6 million lines of code in the kernel and about another 6 in user space. And of those, if you look at the percentage figures, they're pretty tiny. So these are the percentages of lines of code that needed to be changed to move from the baseline software to software that would work and gain protection in CHERI. So of the order of 0.1%, sometimes a bit more, sometimes less. If we look at a language runtime, so here we've got WebKit JSC, right? So there's a port of the JavaScript core interpreter. Here the numbers are a bit bigger, 0.4% lines of code or 1.4% lines of code, although one has to say the changes here were not aimed at minimizing the number of lines of code, right? And also it was done with a slightly old-fashioned compiler, and also this is accommodating multiple different configurations. So one might be able to do, one probably would be able to do a bit better than that. But still, this is not something that requires a massive rewrite into a totally different language. This is something that needs, for example, places where old style C code used long, we need to use int pointer t. Places where old style C code did random bit manipulation to store tags in unused pointer bits, they might need to be rewritten a tiny bit. Things of that nature. Places where the code is using the strange corners of C, not sort of mainline C. Does it increase security? Well, so there's an interesting evaluation by a group at the Microsoft Security Response Center of doing a security analysis of the CHERI ISA by looking at previous vulnerabilities and assessing just sort of by thinking about it, how many of these would be deterministically mitigated by CHERI. And depending what you turn on, that number is between 30% and 70%. Right? So that is by no means all vulnerabilities, but it's a very large fraction of the vulnerabilities. And the variation depends on the feature. So in like a default configuration, maybe you save 30%. If you auto-initialize variables and heap, which in some contexts you do already now for the sake of security, that gets you an extra 12. If you turn on the temporal safety experiments that we have, that gets you up to 67 or so. Some further results about this are going to appear in Black Hat later this year. So this is pretty encouraging. I should emphasize, well, I should mention, so there are multiple potential transition paths for CHERI. So one is what I'm talking about really today is via Morello into the mainline ARM A-class architecture, but one can also imagine transition via CHERI RISC-V or via the ARM's microcontroller architecture. And this has been developed in Cambridge, and there's been a lot of work on this inside ARM. So these are similarly interesting paths. And there's an IP agreement between Cambridge and ARM, the capability essential IP agreement, that ensures that the basic ideas are not tied to ARM. So I think we and they all agree that for CHERI to really be a success, it has to be available everywhere. Right? And you can, if you want to see a sketch of how it might look on x86, then that's in one of our technical reports. Okay, now let me get back to computer security foundations. Well, CHERI is in some sense a new, or at least a new adaptation of the foundations of computing as a whole. Can we place that on a solid footing of mathematics? Can we place that on a solid footing of mathematics from the outset while it's being designed instead of 50 years after the fact? Can we do that in a way that A, provides higher assurance, but also that makes the standard engineering processes easier, not harder? Okay, these are the questions that we on the semantics side asked ourselves. So let's focus first on the architecture specs. Right? So as usual, the specs of the allowed behavior of the hardware and simultaneously the assumptions that you use for programming or for software verification. So there are basically three of these. There's CHERI MIPS, CHERI RISC-V, and Morello. And this is a very attractive target from a verification point of view. Compared to the hardware implementation, the interface spec is very simple. Compared to the high-level languages above it, the interface spec is very simple. It's a narrow waist between the hardware below and the software above. And it's a critical thing, right? If the architecture spec incorporates any security flaws, then any conforming hardware implementation will have those flaws. Right? So we had better get that right. We had especially better get it right in the potential future that Morello or some other processor is sold and marketed on the basis of increased security. Right? We would like any such claim to be founded on some kind of checked truth. So architecture specs, traditionally, they're very large books. Like, you know, this Intel Software Developers Manual, that's like a book about 20 centimeters thick these days. Historically, they've basically been prose and pseudocode, right? Not mechanized in any way. And that means they're usable only as documentation, not for testing or for analysis or for proof. And so that's no good for us. And so we've been doing better, and also partly in parallel and partly together, ARM have been doing better. So for MIPS and CHERI MIPS, we hand wrote rigorous specifications in domain-specific languages, L3 designed by Anthony Fox at Cambridge, and Sewell from some of our team in Cambridge. These are languages specifically designed for specifying instruction sets. For RISC-V and CHERI RISC-V, we hand wrote a RISC-V sales specification that's now adopted by RISC-V International, and we extended it to CHERI. For the base ARM v8 architecture, so a few years ago, ARM transitioned internally from an informal pseudocode to a mechanized language, a mechanized version of their ASL. That was led by Alistair Reed. And what we do is we automatically translate from that ASL into SAIL. Right? So SAIL, as I said, is a language we've designed for ISA spec. It's kind of simple. It's supposed to be as simple as possible in order to have simple semantics that's good for analysis. It's an imperative first order language, so it's like the pseudocode you see in architecture books, except that it has some fancy dependent types because bit vectors of different lengths are ubiquitous in these specs. And from SAIL, we can generate all kinds of stuff. Right? So we have these architecture specs at the top. From them, we generate emulators in C and OCaml that one can use as oracles for testing against. We have a symbolic evaluation engine for SAIL, ILA, from which we use to generate interesting ISA tests that get good coverage. And we can map SAIL definitions into LaTeX, which we use in the documentation for CHERI RISC-V and CHERI MIPS, and into theorem prover definitions, which we use as the basis for machine-checked proofs. So these are basically complete ISA definitions for the sequential parts of the ISA. They include floating point and address translation and so on. And definitions like that have never been publicly available for any sort of production scale architecture. They're kind of complicated. Right? And just to give you a tiny flavor of that, if you look at a single add instruction, if you're only doing formal work in like a simple setting or a relatively simple setting, like for a verified compiler, all you need to know is that the add instruction updates one register with the addition of a register and say some integer. If you look at the full-scale ARM instruction, it has a bunch of options, and to fully specify that, you need some decoding, and then some more decoding, and then the execution, and then some auxiliary functions to access the right register, because that depends on the exception level, and then some more auxiliary functions that actually do arithmetic. Right? So it gets big, but it stays fairly simple. It's just a lot of detail. Okay, so what we do to reason about these is we translate these into theorem prover definitions using kind of using a monadic translation. And for the Coq version, we retain the dependent typing, and for Isabelle and Hall 4, we monomorphize it away. Just to show you what a CHERI instruction looks like, this is actually from CHERI RISC-V. It's an auxiliary function. It's basically the memory load instruction, but it's actually an auxiliary function that's used in that. And you can see down here, it does some loads, and up here, it does a whole bunch of checks that the capability that you're loading on has some specific property. Right? If the tag is not set, then it raises a capability tag exception, and so on. Okay, so I said we were doing lightweight, rigorous engineering. What does that mean? So the first thing that means is that these ISA specs, the formal specs, have been used as the central design documents by the development team, by the hardware and software researchers, not purely by the formal semantics researchers. We use them in the documentation. They're readable enough to do that. We use them as a test oracle, invaluable for testing hardware, for testing emulators, and for software bring-up. We use them for test generation, and we use them for quickly checking properties using SMT solvers. So CHERI started out as a hardware-software co-design project. Since around 2014, we've been doing a hardware-software semantics co-design project. So that means there's a lot of moving parts to keep track of and a lot of people, but it's great fun. You don't very often get the chance to do that. Okay, now, does it actually guarantee any of the things that I've been talking about? Does the architecture guarantee them? What even are they? I've talked about, better security of various kinds. What does that mean? Well, because we have the architecture in a language from which we can generate theorem prover definitions, we can, in principle, do machine-checked proof that specific precise properties actually hold. And that's what we've done. So we, of course, have not proved it that CHERI is secure, but we state some precise properties and check that they really do hold in general for arbitrary code of the entire ISA. So the kind of properties these are, for any intra-domain trace, any execution up to a security boundary crossing, the reachable capabilities from the final state are no greater than those of the initial state. Right? So this captures that design principle that I started off with. Within a properly set up compartment, any trace cannot affect any other memory, and it can exit the compartment only in controlled ways. So Kindle and Nienhaus proved these in Isabelle. These are properties of arbitrary code above the CHERI MIPS ISA with respect to the Isabelle definitions generated from the L3 model of that we had, that we started out with a while back. And we were able to adapt the proofs as the ISA evolved. Okay, for Morello, we wanted to do the same kind of thing, but in a more lightweight fashion. And a key technical device in this is to factor the proof via the instruction local semantics. So if you look just at a single instruction, a capability load, you can look at the register and memory access traces of that instruction. And there are some properties that any capability architecture should have, properties of those traces. Like if you store a tagged capability to memory at some point in that trace, then that capability should be derivable from those that are available at that point. And there's a bunch of other similar such properties. So for Morello, we here is mostly Thomas Bauer-Rice and also Brian Campbell and Thomas Sewell, Alistair Armstrong. We take the ARM definition of the full ISA, the 100,000 line spec, from weekly drops from ARM. We use Sewell to generate theorem prover definitions from those, and also SMT versions. We use SMT to check some quite specific properties about the compression scheme, let's say. We use symbolic evaluation of Sewell to generate interesting instruction tests, which have been used by the hardware design group before the chip taped out, and also for QEMU development. And then again, we use Isabelle for mechanized proofs of similar theorems, factored via those properties. So this found a bunch of security holes, not that many, but certainly some, and a larger bunch of mismatches between different models. So this is machine-checked mathematical proof of some specific key security properties of a full-scale industry architecture at design time, right? Which is not something that we have previously been able to do. It certainly doesn't give you, it's not hardware verification. We haven't proved the hardware implementation correct, but we have gained a lot of confidence that the architecture is correct by doing this. So I'm over time, just to wrap up. Well, let me conclude just very briefly. So we have these in computing, we have these terribly flaky foundations. And in the CHERI project, we have constructed like one very carefully shaped wedge of something somewhat more robust. We are trying as hard as we can to slam into the silt and sand and mud that we're resting on, to hopefully eventually push that tower closer back to the vertical. There's a lot of other work going on which I can't talk about. If you want to know more, here's just a few links to introductory material. And I would like to thank you very much for your attention, and we'll be happy to take some questions.
Thank you very much, Peter. We'll stop the recording now and start the Q&A session.